In this chapter, we will talk about mass percents and empirical formula. This is part of chapter 3 and it's split into two. So in this one, we will do mass percents, and the next one we'll do stoichiometry. So in this case, the first thing we need to talk about is molecular formula and a formula mass. The molecular mass is for molecules, which is the covalent compounds, as we learned in chapter 2, and formula mass is for ionic compounds. Masses are calculated by adding the mass of all elements in the formula, and you get the mass of all of these from the periodic table. Okay, you don't have to memorize them, although as you go on, you will see that you will start remembering a lot of these things. For this chapter and from now onwards, it's really important that you know your nomenclature. Okay, so keep working on it, keep practicing. If you get the formula wrong, then you'll get the problem wrong. Then you get the answer wrong, everything is wrong. So please keep working on your nomenclature. So let's look at some solved examples right now. It doesn't matter what kind of a compound you have, whether you have an ionic compound or if you have a covalent compound, the method is the same, okay, for finding out the formula weight, okay, or molecular weight. I will just call it a compound, not a formula or molecule. Okay, so compound number one, the first one we have here is calcium hydroxide, which has 1 calcium, 2 oxygens, and 2 hydrogens. Again, you have to be good in your nomenclature in order to know this formula. Otherwise, you'll get everything wrong. Okay, so 1 calcium, 2 oxygen, 2 hydrogen. You find the weight of all of these from the periodic table. This is the atomic weight. So you find that from the periodic table, 2 oxygens is 2 times 16, which is the atomic weight of oxygen. And then, of course, for hydrogen, it's again 2 times this because there are 2 hydrogens in here. So you get the multiplied numbers and then you add them all together and you get the final answer. Okay, and so this is the weight of calcium hydroxide. There are two things to note over here. The first one is this number, okay, this atomic weight that you got from the periodic table. Depending on what kind of periodic table you have, you may have up to 3, 4, or 5 decimal places in there. I suggest you work anywhere between 2 to 3 decimal places. After 3 decimal places, it doesn't make a difference in your number, in your calculations. So work up to 3 decimal places for your mass numbers. Okay, that's the first thing. The second thing I want to point out is the AMU. AMU is called atomic mass unit. Since we don't know what these masses are in, like what their units are, so right now we just leave them as atomic mass unit. Okay, we'll talk about what exactly the unit is on the periodic table. Okay, so for now that's what we have. One last thing is make sure you get the right significant figures. Here you were adding up, and so in addition you keep the lowest decimal point. So here we have 2 decimal points. All right, so that's for calcium hydroxide. This one is for methylamine, which is a covalent compound because you see all the non-metals in here. 1 carbon, 1 carbon, 1 nitrogen, 1 nitrogen, and then you have 5 hydrogens. So 5 hydrogen. You find the weight of all of these, multiply whatever we need to multiply, get the final numbers, and then add them together. Okay, so it's very straightforward. Again, your nomenclature has to be good. That's the only way you'll get anything wrong. Okay, otherwise it should be pretty straightforward. The last one is for nitric acid. Along. The mole concept. This is a very important concept in chemistry. This is very critical in understanding how reactions take place. It's understanding what matter is composed of and how do you account for conservation of matter. So my first question to you, what has more number of atoms, 1 gram of helium or 1 gram of gold? Think about it. And the answer is helium. Okay, and it is helium because helium is lighter than gold. So it will take a lot more many atoms of helium to make up 1 gram than gold. Okay, and I'm giving these numbers here for AMU and 197 AMU as grams, okay, just for comparison's sake, but really right now it's all AMU. But if you were to compare 4 versus 197 grams, then obviously it will take a lot more material or a lot more atoms of 4 AMU to give you the 1 gram of helium. Okay, and again, it's a gram, it's an AMU kind of a thing. So right now, the unit is not as important. What is important is the ratio of helium to gold, okay, because that's what I need you to understand, that it takes a lot more helium atoms to give the same mass as gold will. Okay, so why this is so, okay, is because of the weight of gold, of course. So in chemical reactions, what will happen is that atoms will undergo rearrangement. Okay, that's what we talked about in Dalton's atomic theory. So there is no loss of any atoms, which means we need to be able to account for all the atoms. So if we need to account for all the atoms, there should be a way to figure out how many atoms we're dealing with. Okay, and since atoms are so small and so tiny that we can't count atoms, we need to have some sort of number, okay, that we can handle. So Avogadro, an Italian chemist, was the first one who came up with such a number, and he based it on carbon-12. Carbon-12 isotope is one of the purest isotopes of any element. So when we say we have carbon-12 isotope, it actually means carbon 12.00000. Okay, so it's an exact number. And so he used the mass of protons and the charge and all of those things that you studied in chapter 2 to figure out the number, okay, for the number of atoms in a mole. So mole is a measurement that is given to a certain number of atoms. And again, it's a random number, not a random number, but 1 mole is a random quantity. So 1 mole of a substance has 6.022 times 10 to the power of 23 number of atoms. 1 mole is like a dozen, which means that it is a number, it is a conversion factor, it is a quantity. So when you say that you have a decade, that means you have 10. When you say you have a dozen of something, it means you have 12 of something. When you say you have 1 mole of something, it means you have 6.022 times 10 to the power of 23 of something. So 1 mole of people are going to be 6.022 times 10 to the power 23 number of people. 1 mole of pencils are 6.022 times 10 to the power 23 number of pencils, and so on. Okay, so you get the idea that 1 mole is a huge number. You can try and write this number out. 23 zeros, that's what you would need, okay, for 1 mole. That still doesn't help us a whole lot because we still don't know what the mole is, and we still can't count all these numbers, okay, of atoms that we have. 6.022 times 10 to the power 23 number of atoms. That's a lot of numbers to add up, okay, or to count. So what happens is that we relate the number of moles to the mass number of a substance, okay? And so 1 mole of carbon is equal to 12.01 grams of carbon, which then is equal to 6.022 times 10 to the power of 23 atoms of carbon. 1 mole of iron is 55.847 grams of iron. These numbers over here, the 12.01 and 55.847, these are coming from the periodic table. Okay, so these are the mass numbers. This was the number of protons and neutrons in any atom. Okay, so now we're actually giving it a unit. All right, and so this is the mass number from the periodic table, and that mass number is equal to 1 mole. So you can take any element from the periodic table, and that will be actually 1 mole of substance or 1 mole of the element, and that's equal to the mass number of that element, which that 1 mole is then equal to 6.022 times 10 to the power 23 number of atoms. So then the atomic masses, okay, and the molecular mass or the formula mass or all those wonderful things. The atomic mass, let's start with the atomic mass because that's what we have in the periodic table. And so all the units in the periodic table then are reported as grams per mole. So for example, as we said in the previous slide also, for carbon, it is 12.011 grams. But in what? It's 12.011 grams per mole, okay? Because you can definitely have more than that many grams of carbon. You can have 50 grams of carbon, but that 50 grams is not in 1 mole, okay? 12.011 grams is in 1 mole. And that 1 mole is important because that 1 mole will have the same number of atoms, okay? So now when you think about it, the number of atoms is really the important thing. So when you think about 1 mole of carbon versus 1 mole of gold, they are both the same number of atoms. Okay, they weigh a lot more. So here's an example of nitrogen, which is 14.007 grams per mole, which means that there are 14.007 grams of nitrogen in every mole of nitrogen. And this is nitrogen atom. And then sodium is 22.989 grams per mole. So these grams is still in 6.022 times 10 to the power 23 number of atoms. So obviously, because sodium weighs more, it'll have more weight. Okay, that's all. But the number of atoms in both of these are still the same. Nitrogen just weighs less. Okay, all right. It's a very abstract concept in some ways. For us, we're not going to use the number of atoms a whole lot. Initially, you will use that as a conversion factor. In some cases, when you get to electrochemistry later on and some other calculations, you will need the number of atoms. But otherwise, we tend to work more in moles and grams. Okay. Moles again is a unit, but it cannot be measured. Okay, so you cannot go to the lab and say, I want to weigh out 1 mole or I want to weigh out 0.75 moles. You cannot do that. You'll have to convert that into grams. And so we work in gram quantity, okay, of everything. All right, so that's the whole thing here. And again, remember, the number of atoms are important because they are the ones that are rearranging in any kind of a reaction. So instead of dealing with atoms and large numbers like 6.022 times 10 to the power 23, we work with moles. Okay, it's easier to work with moles. All right, so now when we talk about the mass of anything, the molar mass, like what you were doing before with calcium hydroxide and methylamine and all that, now we can work this a little bit more accurately and give it the proper units. We gave these units to be AMU, but now actually the proper unit is grams per mole. So it's the same thing, all right, except now we have grams per mole. Now here we have calcium, oxygen, and hydrogen yet again. So we have the same numbers, the same mass numbers from the periodic table, but now our units are different. And now what this means is that in 1 mole of calcium hydroxide, we have 74.096 grams. Okay, all right. Let's go on. So in the following few slides, we just have a whole bunch of solved examples. And what we're going to do is start converting from moles to grams, grams to atoms to moles, and all permutation combinations possible. Okay, so for example, this is the first one to begin with. A sample of nitric acid contains 0.253 moles of nitric acid. How many grams do we have? So the first thing you'll have to do pretty much for every problem is to figure out the weight, okay, of it, which means that you calculate how many hydrogens and how many nitrogens, how many oxygens, you find out the mass of all of this. You add it all together and you find the weight. Because this is grams per moles, you're supposed to convert moles into grams. So again, this is just a conversion factor, which means what you do is dimensional analysis. What you learned in chapter 1, again, this is just a conversion factor, okay? And so you start with 0.253 moles of nitric acid, multiply that by, you keep the moles down and you keep the grams up because you need to calculate for grams. So 63.02 grams per mole, you do the calculation and you get the answer. Your answer should be 3 significant figures because your initial value was 3 significant figures. All right, so let's work another example now. This one is calcite is a mineral composed of calcium carbonate. A sample of calcite composed of pure calcium carbonate weighs 23.6 grams. How many moles of calcium carbonate is this? So now you're converting grams to moles. Okay, so the first thing that you have to do is you have to find the molar mass of calcium carbonate. 1 calcium, 1 carbon, 3 oxygens. You find all the weights from the periodic table, do the calculation, and find the total weight, which is 100.09 grams per mole. Okay, so that is the molar mass. We call this molar mass because this is what the mass of calcium carbonate is in 1 mole of substance. Okay, so when we say molar mass, that's what it means. Okay, 1 mole of substance, the mass in 1 mole of substance. Okay, so the next find the number of moles in 23.6 grams. Again, you always set up with what you know first. Okay, this is your conversion factor. 23.6 is what you start with. Okay, and so here we are, 23.6 grams, put the grams down, moles goes up here, and this is the answer you get after doing the calculation. Again, this is not the right significant figures, it should be 3. So that's your final answer. Okay, 2.36. If you want to give this in exponent form, that's fine. If you want to give it in this form, that is fine too, so long it has the right significant figures. The next one, again, 2.2 grams of an amino acid, leucine, and what is the average daily requirement of leucine in moles? Okay, and so here we go. Find the total mass, okay, of leucine first, because that's what we give, that's the conversion factor that we need in grams per mole. So in leucine, we have 6 carbons, 2 oxygens, 1 nitrogen, and 14 hydrogens. And find the mass, okay, of leucine. The total mass is 132 then, and then go ahead and set up your problem just like before. Okay, 2.2 grams is the number that's given to you. You use the 132 as your conversion factor over here. You get the mass, convert it to the proper significant figures. Okay, it should be as simple as that. All right, the daily requirement of chromium in a human diet is 1.0 times 10 to the negative 6 grams. How many atoms of chromium is this? Okay, so now in this case, you find out the mass. Now this should be atomic mass of chromium because you're just talking about chromium as an element, okay? But it's written as molar mass because again this is 1 mole, okay, mass of chromium. So here is that mass, 51.996 grams per mole, and then you need to convert the grams to moles. Remember, there is no direct conversion between grams to the number of atoms. Okay, you literally will have to take everything into moles and then convert it into atoms or whatever else you need it for. So you start with 1.0 times 10 to the negative 6 grams, convert that into moles first as we have been doing previously, and then convert that number of moles into the number of atoms. This is Avogadro's number, pretty standard. I will give you this number and I'm quite sure you will never forget this number from now onwards, but this is how you set up the problem then. Grams, grams cancel out, moles, moles cancel out, and you're left with the atoms of chromium. Your final answer is this many number of atoms, 1.158, but of course this is not correct because we need 2 significant figures, so here is your final answer, okay, for the number of atoms. So this is the number of atoms of chromium you need every day, okay, for your system. All right, so this is a 3-step or 2-step conversion, okay, as we say. Mass percents. To calculate the mass percent of each of the components in a compound, you have to find first the total mass of the compound, which you will find from the periodic table. And then to find the mass or the percent mass of an element in that compound, you will find the moles of the element that are present in that compound, multiply it by the atomic mass of the element, and then divide it by the molar mass of the compound, which is the total mass of the compound, times 100. So for example, if you were trying to find the mass percents of sodium carbonate, you have 2 moles of sodium, 1 mole of carbon, and 3 moles of oxygen. To find the mass percent of sodium, you would have 2 moles of sodium times the mass of the element, which is sodium, and that's 23, and then the total mass of the compound, which you have to calculate. In the following slides, we have some examples for you to work on. Lead chromate is used as a paint pigment. What is the percent composition of lead chromate? Now, when we talk about percent composition, it means you need to find the percent of each of the substances in there. Okay, so first you find the mass of lead chromate, which is PbCro4. Okay, that's given to you. Remember, chromate is not one of those polyatomic ions that I asked you to memorize, so I will give you the formula of those. The ones that I asked you to memorize, you must know them. I will not tell you what they are. Okay, so find the total mass and then convert each to the percent composition. Okay, so for lead, chromium, oxygen, all of these. So what you do is you take the mass of lead and you divide it by the total mass times 100. The percent for chromium would be the mass of chromium over the total. Then for oxygen, it would be the mass of oxygen over the total mass. Find the percent, multiplied by 100%, and these are the percents you get. A quick cross-check for doing mass percents is that you add up all your percents and you should get a total of 100%, okay, because each of these is a percent, okay, of the total compound. So that is how you figure out the percent composition of each of the elements, okay, you have in a compound. All right, so now this is a little bit different kind of a problem. So the chemical name of table sugar is sucrose, C12H22O11. How many grams of carbon there are in 68.1 grams of sucrose? Now you're just focusing on grams of carbon. You're not focusing on the entire glucose, or excuse me, sucrose. You still need to find the mass of sucrose, okay? But you need to find out how many grams of carbon there are, okay, in the sucrose. So first of all, the molar mass, okay, you do need that. So 12 carbons, 11 oxygens, 22 hydrogens, add that up all together. You get a total mass of 342.296 grams per mole, okay, for sucrose. Now you have to find out the mass of carbon in 68.1 grams of sucrose. So guess what? You got to start with 68.1 grams of sucrose. In 1 mole of sucrose, you had 144.12 moles, okay, of sucrose, of carbon in there. This is the percent actually, okay, if you think about it. So this is how many grams of carbon you have in 342 grams of sucrose. So in 68.1 grams of sucrose, you will have to find that proportion. And that is 28.7 grams of carbon then. All right, so if you did not have this number, you will not be able to do the calculation. Now, if the mass percent was given to you, then you would be able to do it. So here is an example of a percent hydrate calculation. This is a kind of a lab you will be doing, and in that you will be taking a hydrate and you will heat it to remove the water. You will not know how much of water there is, so that is your lab assignment. But here you actually have the hydrate and you're calculating the percent of water in that hydrate. So the way you calculate it is the same way, which means that you first find the entire molecular weight of the substance. So copper sulfate, 1 copper, 1 sulfur, 4 oxygens. That is the main salt. And then of course the water also, don't forget. So we have H2O, 2 hydrogen, 1 oxygen. You add that together, 18.02. And when you're trying to find the total mass, it will be the copper sulfate, copper 2 sulfate, and the 5 water because it's pentahydrate. So you find the total mass of the compound. To find the percent of water in the salt, you will have to take just the water molecules on the top divided by the entire formula mass, which is the mass of the salt plus the water, and times 100%, and that gives 36.08% water, which is actually a lot of water. But that's how this is. And this is the kind of lab you will have. You will have to do a back calculation, which means that you will actually find out what percent water you have in there. And then you will find out what hydrate you have from the list of unknowns, okay, given to you in the lab. So here are some more examples for you. First one, determine the number of moles. Again, just a mole calculation. You've done this before. From grams. Here's another one, determine the number of molecules from moles. Again, your molecules will be 6.02 times 10 to the power 23 molecules, okay, of this molecule, which is C2H5OH, okay, which is ethanol. And so mole conversions right here directly to molecules. And then the last one here is how many H atoms there are in our hydrogen atoms there are in 4.6 moles of ethanol. So you have the moles of ethanol from here. Okay, that's the number of molecules of ethanol you have given in 4.6 moles, and you have 6 hydrogen atoms in one molecule of ethanol. Okay, 5 plus 1, so that's 6 atoms. So you have 1.7 times 10 to the power of 25 atoms of hydrogen in 4.6 moles of ethanol. So it's just a few other examples for you to work on and think about. Okay. Combustion analysis is a very interesting thing. It is a way to find out what kind of elements are present in a compound. These are typically for organic compounds, and organic meaning something that is covalent bonded, okay, on the right hand side of the periodic table. And so the elements that you study in this are carbon, hydrogen, nitrogen, sulfur, and sometimes oxygen. And you will see what I mean by sometimes oxygen, okay, in just a second. But what you do is you take the sample and you combust it, which means you burn it in oxygen, and you have different collection points for different gases that are evolved. So for example, if you have carbon in there, then carbon dioxide will be forming. If you have hydrogen in there, then water will be forming. If you have nitrogen, you will have nitrogen oxide that's forming. Okay, so everything is adding on oxygen. So you collect all of these gases, you take the mass of all these gases, and then you find out how many grams of carbon you had, how many hydrogens you have or nitrogen you had in your original sample. Okay, and over here when I said sometimes oxygen, and that is because you cannot burn oxygen to give more oxygen, which means that when you get your total mass, then you have to subtract and figure out and see if there's anything missing. The missing mass is going to be for oxygen. Okay, all the other elements are going to burn in oxygen except for oxygen. Okay, so this is what we call combustion analysis, and this is a very common technique that is used in chemistry departments to figure out, or chemistry research, to figure out what the formula is for any kind of a combustion. So, calculating the empirical formula, okay, of anything. Empirical formula is, if you remember, the smallest ratio, okay, of anything. Molecular formula is the actual formula. Okay, so empirical formula for N2O4 dinitrogen tetraoxide is NO2. This is the simplest formula. Empirical formula for hydrogen peroxide, H2O2, is HO. Okay, so what we use the combustion analysis is to figure out the empirical formula, and then you have to do one more analysis to figure out the actual formula, okay, which is the actual molecular formula of the compound. So this is a whole lot of things that are written out here, but unless you solve a problem, you will not know. Okay, so keep this handy. And so as we go on, all of these points that I've written out here for you, they will start making sense. Okay, so you really have to just solve a problem, okay, to figure out how to use these. Okay, so let's work out an example for combustion analysis. Here is a question. Benzene is composed of 92.3% carbon and 7.7% hydrogen. What is the empirical formula? And then if its molecular weight is 78.1 AMU, then what is the molecular formula? You start with what you know, which is carbon and hydrogen percents. If you look at these two percents, they both add up to 100, which means benzene only has carbon and hydrogen. If anything was missing in here, that would have been oxygen. But right now, this is it. Okay, you have just carbon and hydrogen. So the first thing you do is you find moles. You take the percent of carbon and percent of hydrogen and convert that into grams. Okay, so you assume that you have 100 grams of substance, and in 100 grams of substance you have 92.3 grams of carbon, 7.7 grams of hydrogen. You find the mass from the periodic table of carbon and convert the 92.3 grams of carbon to moles, which gives you 7.685 moles. You do the same for hydrogen. You find the moles of hydrogen. Once you have this, the next thing to do is to take the smaller number of moles and divide the other numbers by that small number. So at least you have one number that is a ratio of 1. All right. But in this case, it turns out that if you take the smaller number 7.64 and you divide the moles of carbon with it, you still have 1. Okay. And so the ratio of carbon to hydrogen is 1:1. And so your empirical formula is CH, where carbon to hydrogen ratio is 1:1. To find out what the molecular formula is, you need to first calculate the mass of CH, okay, which is going to be 1 carbon plus 1 hydrogen, that is 13, okay, 12 plus 1, that's 13 AMU. The molecular weight of benzene was given to us, which is 78.1 AMU, and so you take 78.1 and divide it by 13.02, which was the weight of the empirical formula, and then you come up with this number, which is 6, which tells you that the molecular formula and the empirical formula is a ratio of 6:1. And so you multiply then the empirical formula by 6 and you get C6H6. So the empirical formula for benzene is CH, the molecular formula is C6H6. One point to note over here is that you would not have figured out the molecular formula if you did not know the molecular weight, okay, of this. So that's what I was saying, you need another instrument to figure out the molecular weight of the compound, okay, because if this is not known, then you cannot figure this ratio out, okay. Here is another example, similar. So here you have sodium pyrophosphate, which is used in detergents. It has sodium, phosphorus, and oxygen. So it has 3 elements. And again, a quick addition of all of these 3 tells you it's a total of 100%. Okay, so oxygen has already been accounted for over here. What is the empirical formula? So again, what we will do is we will convert all the percents to grams. Once we have all the grams, then we will convert that into moles, okay, using the gram weight from the periodic table. So once you have all the moles, your smallest number here is 0.7523. So you will divide all the numbers with that small number, and that is how you get the ratio. Okay, so 0.7523 is your smallest number. So you divide all the moles, okay, with that smallest number, and this is the ratio that you get. Okay, now in this case, sodium is a nice whole number, 2. Phosphorus is 1 number because you're dividing it by itself, but this is 3.5. Oxygen is 3.5. Now remember, according to Dalton's atomic theory, you cannot have half an atom in any formula. So what you'll have to do is you will have to multiply everything by 2 to get rid of that half. Okay, so it's removing fractions. Okay, that's what we have to do. So multiply everything by 2. So 4 for sodium then, and 2 for phosphorus, and then oxygen will be 7. And so finally your empirical formula is Na4P2O7. Okay, so that is how you work out an empirical formula. Here is another example. In this case, you have carbon, hydrogen, and nitrogen. And again, the molecular weight is given to you, so which means you have to find the empirical formula as well as the molecular formula. Okay, so here we go. Convert everything to grams, convert that into moles. Once you have the moles, you divide it by the smallest number, which in this case is 1.72. So then you get the ratio. So your step number 3 is your empirical formula, okay, which is C3H8N. After finding out the moles from here and the mole ratio, you find the weight of the empirical formula, and that is 58. Your molecular weight is 116, so you do the division, and that is 2. 116 divided by 58 is 2, which means that you take your entire formula and you multiply that by 2. So it gives you C6, H16, and 2. Your keywords and concepts for this one really is formula mass, mole concepts, Avogadro's number, mass percents, elemental analysis. Okay, it's a whole bunch of calculations. So really there are not that many keywords for this one. Okay, it's practice with the calculations. All right, have fun with the calculations.